I recently had someone ask me about why block sizes were important in cryptography, and when I referenced the birthday problem, they didn't really know what that was, and so I thought I would make a little video kind of showing the birthday problem from a mathematical perspective, purely mathematical, and then kind of show its applications in cryptography. So what is the birthday problem? The birthday problem is a problem based on the probability that any two people and a set of n people would share the same birth date. So if you had 50 people, it's kind of the probability of two of those people being born on the same day of the year, like January 1st, January 2nd, 3rd, so on. The issue is that you have a potentially unlimited number of inputs, people, with a limited number of outputs. There are only 365 days. Even if there's 700 people, 1,000 people, 1,000,000,000 people, the number of days doesn't change. The more people there are, the higher the likelihood that two are born on the same day of the year. When there's two people, it is not very likely they have the same birth date. And then as you go up, it gets increasingly likely very quickly. This is the pigeonhole principle. When there are X inputs and Y outputs, if X is greater than Y, some number of inputs, they have to share an output. So, for example, if you need to carpool somewhere with a group of people, and you had, let's say, 6 cars and 10 people, multiple people will have to share a car. There could be cars with one person. There could be cars with 0 people. There could be cars that are left empty. You could, for 10 people, you could get 2 people in 5 cars. 2 people per car in 5 cars to make that the 10 people. But no matter what, if all 10 people have to fit into those 6 cars, there must be more than one person in at least one of those cars. So let's actually calculate the probability. To determine how likely this is, we can use the following equation, where n is the number of days in this case, and k is the number of people. So the first number we need to get is v of nr, and that's equivalent to n factorial divided by the quantity of n minus k factorial. And then for the second number, we need n to the power of k. Our answer is v nr over vt, and the reason we subtract that from 1 is to get the probability. So what we're actually calculating is the probability that it doesn't happen. This is based on permutations. This is a standard permutation equation. And because this is a probability, 1 would be 100%. So if our result is 1, it is 100% going to happen. If our result is 0.5, it is 50% likely to happen, and so on. So as an example, when n equals 365 days and k equals 33 people, we can see n factorial over n minus k factorial is 365 factorial over 365 minus 33 factorial, and that comes out to roughly, this is rounded, 8.089121 to 80, like scientific notation, 83, so times to the 10 power 83. And then for VT, we have n to the power of k, which is 365 to the power of 33, which is roughly 3.594715 times 10 to the 84. So for the probability, we would subtract our VNR over our VT from 1, and we would get 0.2250. So subtract from 1, we get 0.7749. So in a group of 33 people, there is a 77.49% chance that 2 people share a birthday. This equation can be more simply rewritten as n factorial over n minus k factorial times n to the power of k. And this is because if you take a look back up here, if we were to divide these out, but multiply, division by multiplication instead, for n to the power of k, we would have in the numerator, we would have n factorial times 1 over n to the power of k. So if you multiply these out, you would have 1 here. So n factorial times 1 is 1, and n minus k factorial times n over k is n minus k factorial times n to the power of k. This is relatively simple math, so if it looks scary in notation, there's just a couple really simple things to note. So 365 factorial, or with an exclamation point, is 365 factorial, which means 365 times 364 times 363, all the way down to 1. You don't go all the way to 0 because obviously if you multiply by 0, you would just cancel the whole number out. Much of the numerator and the denominator do tend to cancel out in these cases. So for example, if you had 365 factorial over 364 factorial, it is just 365 because you have 365 times 364 times 363 times 362 divided by that same string just starting one number lower at 364. And for a simpler example, because obviously we don't have space to do 365 factorial, if you had 7 factorial over divided by 6 factorial, you would have 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 6 times 5 times 4 times 3 times 2 times 1. And you can see here that these would just cancel out, which would leave 7 over 1. So what does this have to do with cryptography? What this problem illustrates is that we have a permutations limit. There's an upper bound on the total of number of unique ways we can represent an output. The fundamental issue is that for any given fixed length output, there are only so many permutations available. With computers, this is usually 2 to the power of n, with n being the number of digits available. Why 2? Well, transistors can either represent a 1 or a 0, which means you can represent one decimal place or order of magnitude per transistor, with it being one of 2 values. So per transistor, you can represent 2 separate distinct values. Consider a one-place binary number, like, where's my mouse? Right here. Like this. We can represent 2 things. We can either represent 0 or we can represent 1. We can now represent 2 to the power of 1 values, which is 2. 2 values, 0 or 1. What if we add a second digit? We can now represent any of 4 values. We can represent 0, 0, 0, 1, 1, 0, or 1, 1. This is represented with our 2 to the power of n rule, as 2 to the power of 2 is 4. So here we can see once we add a second digit, we can represent 4 values. Now let's toss in the third. We can represent 8 values with this, 2 to the power of 3, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, or 1, 1, 1. Again, 3 digits, so 2 to the power of n is 3, is 8. 1, 2, 3, 4, 5, 6, 7, 8 different values. So think about how these places work in the number. With 0 and 1 digit, you can represent 2 numbers. When you add a second digit, you can represent all the prior possibilities twice because it's binary. If it was base 10, like decimal, you would be able to represent 10 times as many. Moving from 2 to 3 bits, for example, you can represent all 4 possibilities of 0, 0, 0, 1, 1, 1, and 1, 0 twice because all 4 values exist for 1 and for 0. So when the third digit is 0, you can represent all 4 of these values as, themselves. And then you can flip the first bit. So instead of being 0, it's a 1. And you can represent all those values again. So you have just doubled the number of values that you can represent. So this limitation is present in all forms of computing. Consider for a moment signed and unsigned numbers. A 4-bit unsigned number to represent 3 looks like this, 0011. This can represent 2 to the power of 4 numbers, or 16 total numbers. However, to sign the number, we must sacrifice 1 bit, the first bit, and to denote the positive or negativeness of the value. So usually, like in this, it would be, if this was a positive value, this would be 0. And if it was a negative value, this first high order bit would be 1. So we now end up only being able to represent either negative 2 to the power of n minus 1 numbers or positive 2 to the power of n minus 1 numbers. In this case, because this is a 4-bit number and we're sacrificing 1 bit, we only get 3 bits for numerical representation, and therefore we get 2 to the power of 4 minus 1 or 2 to the power of 3, which is 8. Now, signed numbers are a little wonky because 0 is counted both ways. So you technically can only represent 15 values with this because you can represent 0, 1, 2, 3, 4, 5, 6, 7, 8 as a positive, or 0, negative 1, negative 2, negative 3, negative 4, negative 5, So with a signed number, you can never represent a number greater than 7. You can't represent 8, 9, 10, 11, 12, 50, 100, 1,000. Positive 7 may be 0, 1, 1, 1, and negative may be all ones. And as a side note, positive signed 7 and unsigned 7, the reason why it's important to know whether a number is signed or not is because they look the same, so you may treat them differently. And a signed negative 7 and unsigned 15 look the same, so it's really important that when you're dealing with data types in a program, you know whether a value is signed or unsigned, because obviously negative 7 and 15 have very different values. So another thing to do with, having a limited number of representation is consider why 32-bit operating systems can only address 2 to the power of 32 bytes of RAM without special register tricks. I mean, you can, put two registers together and read the address out of both of them. There's all kinds of wonky things you can do to get around it. But, in general, so you can tell a system to look from address. I'm not going to say all these numbers, but this is 32 zeros all the way to 32 ones. So you can have all zeros and then 1, and then all zeros and then 1, 1, and then all zeros and then 1, and then 0. And those all represent a different address. But after that, you cannot represent any more addresses without a repeat. With a 64-bit operating system, you can have 2 to the power of 64 addresses or 16 exabytes of RAM. Now, think back to how every single time you add a digit, you can represent every number you've already represented twice. So the reason that extra 32 it's a power of 32. That's why it gives you such a large increase in size. So 2 to the power of 33 could represent every one of these addresses, both of these and everything in between them, and then you would add another bit in front, and you could represent, if that was 0, you could represent all these addresses again, and then flip it to 1 and represent every single address again. So concomitantly, hashes and block ciphers suffer from the same representation issue. Take a hash like SHA-1, for example. It is a 160-bit hash, meaning it can produce 2 to the power of 160 different outputs. And that means, 160-bit means that it outputs basically 160 zeros or ones. So this is 32. You can imagine how long that would look. This means there has to be inputs that generate identical hashes. All else being equal, the longer the output length in bits, the less likely you are to find two values that create two identical hashes. When you do find two separate non-equal values that create an equal hash, it's called a collision. Once more than 2 to the power of n hashes are created, it must repeat an already created output since it cannot represent any more values. The same hash must represent two different values. This is an inherent issue in hashing because if you think about the number of possible documents you could have or hashing information sources, there have to be things. There's more than there are kind of the X and Y thing, right? When you have X inputs and Y outputs, if there is more X's than there are Y's, you have to have something that goes into the same container. If there's 10 people in 6 cars, more than one person has to go into at least one of the cars. It's the same thing with hashes. When you have more possible hashing inputs than possible hashing outputs, more than one hashing input would have to map to the same hashing output. So block ciphers suffer from the same problem. Now, modes of operation change this a bit, but block ciphers take an input of a fixed length and give an output of the fixed length, and it's the same length. Whatever the input is, the output has to be the same length. So, for example, a block cipher with a block size of 8, which is much smaller than you would ever use in practice. This is just so we can wrap our fingers around the numbers a little bit easier. If it was a block size of 8, we will take an input of 8 bits and give an output of the same length. This means that 8 bits are encrypted at a time. Let's take, for example, lowercase d in ASCII. Trying to find my mouse. There it is. Lowercase d in ASCII. This is 011000100. So this would be the input in this case. Now we may encrypt it, and once we're done encrypting, we may get an output, for example, like 0111011, which is lowercase w in ASCII. This will change based on the key. So for any fixed key, there are 2 to the n possible values where n is the block size, or in this case, because the block size is 8, there is 2 to the power of 8, or 256 total unique values. Each key should give one unique output for each input. This is a bijection, which is essentially like a one-to-one function. With different keys, there are at most 2 to the power of n factorial different bijection sets. So you cannot have any more, so 2 to the power of 8, 256 factorial would be the most number of different one-to-one mappings you could have for this. So now understand that in block ciphers, repeating blocks can divulge information. Once there is a collision, and a collision in a hash and in a block cipher, it means the same thing, but it has different implications. So it is essentially that you have a repeat of an already generated block or already generated hash. It is possible to start extracting plain text once you get that collision in block ciphers. How this occurs depends on the cipher and the mode, but just know for now that collisions are generically a potentially very bad thing, and we can go over that another time about how you can extract information from that and how it degrades security of the cipher and all that kind of stuff. The birthday problem comes into play when you consider that you're not looking for the maximum number of unique values, not that 2 to the power of n, but you're looking for your probability of getting an equal pair of values, so a pair that you've already generated. So remember how likely it was that a pair of individuals in a group of 33 people shared a birthday despite 365 possibilities? So with only 33 people, you have a 70% plus chance of a pair of an already, it's called a generated birthday, despite that's less than 1/10 of the number of possibilities. We have a similar issue here. So let's say we have a cipher with a 32-bit block size. We can quickly approximate how many blocks we would have to generate to reach the birthday bound by taking the square root of the total possible outputs. This birthday bound means there would be an around 50% chance of a collision. So whenever we're talking about a birthday bound with these ciphers, we're just looking at when is it more likely than not, even just by a little bit, 50.00001%. How do we get to the place where it's more likely than not that I would repeat a block that I've already generated? In this case, it would be the square root of 2 to the power of n, with n being the number of bits. Now remember, that's an exponent, so when you take the square root of that, you just divide it by half. So it could also be rewritten as 2 to the power of n divided by 2. In this case, because we have a 32-bit cipher, we can do this by the square root of 2 to the power of 32, which is 2 to the power of 16. That's only 65,536 blocks. If we were encrypting 32 bits at a time, or 4 bytes at a time, this would only give us 262,144 bytes, or 256 kilobytes, before we had a more likely than not to risk a collision. So this is very small, right? If you look back at the ASCII, right, these are 8 bits a piece, so 1 byte, and that means you could encrypt 4 letters in a total of 65,536 blocks before you would be very likely that more likely than not, that you would generate a block that you've already generated. And that would lead to a collision attack. So is this attack realistic? It is. The Suite32 attack, which you can go to suite32.info, published in 2016, can recover the cookies of 64-bit ciphers used in TLS after about 758 gigabytes of information being transferred, and it can take less than 2 days. And remember, there are a lot, that's total data transmission. So if you were doing video serving, or you were serving large files or receiving large files or doing a lot of communication, this is not a completely unrealistic attack. That being said, most encryption uses a mode of operation that modifies the key after each or several encryption rounds with either a tweak value like an XTS, an initialization vector, which is like the classic, you think of CBC or any of those like very classic ones, or a nonce, which means a number used once, n once, number once. And that's like encounter mode and things like that. So I hope this was helpful, and I hope you have at least surface level understanding of the birthday problem and its applications in cryptography.